In this particular talk, we're going to be discussing how we can deal with irregularly shaped channels and conduits in FlowMaster. In some of the earlier ones we talked about, we dealt with normal shapes such as circular channels or trapezoidal channels. And while those calculations can be a bit tedious manually, working with irregular channels is very challenging. Trying to do manual calculations, you really need a tool that can help you handle irregularly shaped channels. So what we're going to do now is run through some examples. We'll take let's say a combined sewer, one of these old combined sewers, and look at one of those and how you might model that. And then we'll take a natural channel, let's say something approximating some type of stream. So we'll go to the usual place where we start a new worksheet, which would be new worksheet. And this time we're going to go to pipes. And again, pipe is really very generic here. It's anything that has a top to it, essentially, can be called a pipe. So let's go to irregular channel and go this way. Okay, so this is the dialog, which looks like a lot of the other dialogues that we have for FlowMaster. But we have some more information. We see down the bottom here, we have to define the irregular section. Okay, so let's give it a channel slope of, let's say, 0.01. This will be what we might find as an old brick sewer that might have a very mild side slopes, but then there'll be a deep trickle channel down the middle for very low flow conditions. So what we have to do now is define the overall cross section. So we go to the bottom of the dialog here and see edit section at the bottom. So we hit edit section, and this opens up our dialog for creating this particular section. Okay, so we'll start at station 0 just to make that easier and give that an elevation of, let's say, 6 feet. So we have a 6 foot high, big combined sewer. It's going to have we'll look at the shape of that. And right at that, this is the sidewall. It goes down to about 2 feet high. And then there's about 4 feet that gradually slopes down to 1 foot high. Let's see as we start building this channel. And then 4 to 5 feet, at 4 feet there is a drop down into the trickle channel at the bottom. That channel is 1 foot wide, so we have another point down there. Then at 5 feet it goes back up to 1 foot. And then from 5 to 9, it goes back up to 2 feet. And then at 9, we have the other side of the combined sewer. All right, so that was pretty easy laying out the cross section for one of these combined sewers. Again, dry weather flow runs down this bottom channel, and then when you get wet weather flow, the flows can increase dramatically. This happens in a lot of combined sewer systems. Now, one of the other things you can do with this, though, is you can specify different roughnesses for different parts of the channel. So starting at 0, we're going to go with the very first one and give it a roughness. Let's say this is some type of brick sewer, so let's give it a roughness for Manning's equation of 0.02. Then starting at 4 feet and going across that small channel, we're going to go to 0.015, just because we can. And then starting again at 5 feet, over to the end of the channel, we'll go back to the rougher bricks. Okay, so now you can see where we have different ranges here. These little points show you where you transition from one type of roughness to the other. So you say, okay. The hydraulic slope of the channel is going to be about, let's say, 0.01, about a 1% slope. We're going to let that be 0. And we can now determine the discharge rate. Got to put an elevation. Okay, got to put how deep the water is relative to the bottom, of course. And let's say we have 2 feet of water in that channel. Okay, what's the discharge? It's 30 CFS. So we can look at that cross section now. Go to our cross section editor, open it up, and we can see what it looks like when we have the depth of 2 feet in that channel. So we want to see. Let's just go back and say how much water can we carry while we're still in that trickle channel, that 1 foot deep channel. So that one. We see we could carry about 4 CFS in that low flow channel. So let's look at that cross section. Okay, so there is the cross section. It shows we get about 4 CFS during this in this low channel, and then we want to see how much we can carry all the way full. We can put this to an elevation, let's say 5.99, and see how much flow we can have. Boy, that's 500 CFS we can carry. And look at the cross section there, and that's where it's pretty much full. Again, we have the usual kind of calculations of auxiliary values, such as hydraulic radius at these different flow rates, wet perimeter, and flow type. We see it's supercritical in this case with fluid number. It's just a little bit above 1 for this particular channel. If we lowered it back down to, let's say, that 2-foot depth we started at, we see that it's more supercritical by a little bit more. The velocity here is about 5 feet per second. So the velocity doesn't depend too much on the depth in this particular case. All right, so that's an irregular channel you might find in a combined sewer. Now let's go to the case where we're looking at a different type of irregular channel. We'll go up here to New, Worksheet, and we'll pick an open channel. Okay, and go with an irregular open channel. And in this particular case, we're going to look at some type of natural stream. Okay, so we're going to look at a much milder slope. Let's go to 0.002 for the slope of the channel. And we're going to pick a, let's see what happens when we have a depth of, let's say, 6 feet in that channel. So we've got a much larger channel in this particular case, and it could have all kind of shape to it. So let's go to stations. Let's put stations in about every 20 feet in this white channel. 20, 40, 60. Okay, so the elevation at the edges here are going to be, let's go to 10 feet at each side of the channel. And then in between we have a kind of a very gradual slope at first. Then it dips down to, let's say, 2 feet, and down to 1, and we'll come up to 8.5. So here is our irregular channel that's what's out there naturally. We can put in as many points as we have data for. And again, the first 2 channels might be kind of rougher, a lot more vegetation. So we'll go from our first situation, might be, let's say, a Manning's end of about 0.04. And then from the point at, let's go to about 20, it'll drop down to a smoother flow of 0.03 for Manning's end. But then picking it up at location 80, we'll go back to that. Let's say it's even rougher on that side, 0.05. Okay. Now we've defined the channel. We've set up 3 different roughness ranges. We go back in and put in a water depth. Let's say 6 feet of water depth. And you see it'll carry 690, almost 700 CFS and a velocity of 4 feet per second. And you saw how easy that was. I mean, if you've ever done these calculations by hand with these different sections and have to look at different Mannings in each section of the channel, it can be very tedious, the calculations. And we just did that very easily. And we could look at the cross section as we like and see what the flow looks like. Now this again is exaggerated scale. You have the options of changing the scales, the height and width. This is the default condition as far as showing you what the water depth looks like. And we can also go and do a rating curve for this channel. Okay, so let's look at the discharge versus water surface elevation. I think our lowest water surface there was about 2 feet, and we went all the way up to about a 10-foot depth. And we'll do that in increments of 1 foot. And boom, now there's our rating curve of water surface elevation versus discharge. A very long, tedious calculation if you're doing it manually, but with FlowMaster, it's a pretty easy calculation. So it just showed you how to handle some irregular channel problems, which are very time-consuming and tedious problems if you're trying to do them manually. But doing them with FlowMaster, they're pretty much a snap. Thank you.